Hello and welcome to Tonight at 8 from the RSGB. Radio amateurs are used to thinking about the practical side of radio with antenna, feeders and the rig itself. But central to our hobby is the radio wave. Our guest presenter tonight is Peter Duffett-Smith, GM3XJE, and as well as being editor of Radcom Plus, he also sits on the RSGB Propagation Studies Committee, so is well placed to help us understand the radio wave and how best to use it in our hobby. So welcome to Tonight at 8, Peter. Can you give us a quick overview of what you'll be talking about this evening?
Yes, thank you, David, and hello, everyone. Thank you for tuning in. I want to talk about radio waves and how we make them. So we'll be looking at the underlying principles which apply and which we radio amateurs perhaps should all be aware of. So we'll be starting with the radio waves themselves, and then we'll be examining antennas, and I hope showing us all how to understand them and how to get the best out of them.
Well, we're looking forward to that, Peter. And before your presentation, a reminder to everybody at home that if you're watching this on Monday the 4th of July, then this is live and you can ask questions and make comments on either BATC or YouTube chat at any time during the presentation or straight afterwards. Please include your first name and call sign if you have one within every message. And note that you can usually make this video stream fill your screen on most devices, usually by double-clicking on the picture or pressing the full screen button. But now, back to Peter for radio waves, antennas and all that.
Okay, so we start with the radio waves themselves. What are they? Well, I was watching a television program last night about, it's Brian Cox giving a presentation about the rover looking for life on Mars. And despite the fact that we can put a rover on Mars, radio waves are still not fully understood. We have ideas now which include concepts like photons and quantum physics, but these ideas are not very helpful to us radio amateurs because we simply want to use radio waves for communication. Radio waves are electromagnetic waves, and electromagnetism in general, and radio waves in particular, are extremely well described by a set of equations called Maxwell's equations. And we can use them to analyze and exploit, but they don't explain what's going on. You'll see in a minute how even a simple radio wave propagating through space has a mysterious property. So let's imagine that we are in outer space, a very long way away from anywhere. There is nothing here. It is a vacuum. But right over there, 1,000,000 miles away, there is a powerful radio transmitter which is making a continuous transmission at, say, 10 megahertz. As the radio waves pass us by, let's imagine that we take an instantaneous snapshot of the electric and magnetic fields. This is what we might see in our electromagnetic photograph. The first thing to note is that the electric and magnetic fields are in phase with each other. So when the electric field is as big as it's going to be, then the magnetic field is also as big as it's going to be. Here in this diagram, the electric fields shown by the vertical arrows and the magnetic field by the horizontal arrows. And the direction of propagation is also shown, the direction of travel. And you can see that all of them are inclined at 90 degrees to each other. So we have a 90-degree inclination between the electric and magnetic fields and a 90-degree inclination between both of those and the direction of travel. Now, each of these fields carries half the energy of the wave, so both are equally important. You can't have a radio wave which is only electric or only magnetic. The energy is divided equally between both. Now, let's zoom in on one particular place. Here we are. It's shown by the red circle on the diagram here. And look right there. There is no electric field and no magnetic field. At this particular moment, there is nothing at this particular point. It's a vacuum. There's no medium, there are no molecules, there is absolutely nothing. Yet a moment later, the electric field grows and the magnetic field grows as the wave advances. So this point at which there is nothing at all has known that it must grow fields. Now, this is quite unlike any other wave in classical physics. For example, the ripple on the surface of a pond involves both the displacement and the speed of the water molecules. When the displacement is zero, as the electric field and magnetic fields are both zero at this point, when the displacement is zero, the molecules are moving at their greatest speed. So the energy of the wave is maintained as kinetic energy of molecules. But look, in this wave, we don't have anything at all at the 0 point. So no energy. Where's it gone? How does it do it? Well, you know, Victorian scientists were troubled by this, and they invented an imaginary medium called the ether, the all-pervading medium in which electromagnetic waves propagate. However, despite persistent attempts to measure the ether, for example, the Earth's motion through it, it has never been detected and has rather gone out of favor. We perhaps don't need it anyway if we think of the propagation of radio waves as the propagation of gazillions of photons. Now, another problem for Victorian physicists was the fact that radio waves travel in a vacuum. Measurements of speed are always relative to something tangible. You know, you say the train is traveling at 100 miles an hour relative to the tracks. And if you're stationary with respect to the tracks, the train passes you at 100 miles an hour. But if you're traveling at a steady speed, that is, no acceleration in outer space, there is nothing to measure your speed against. Indeed, there isn't any meaning to speed at all. Suppose you fire your rocket motors and you accelerate for 10 seconds, and then you turn off your rocket motors. So you've gone from one steady speed to another steady speed. Well, your state is exactly the same as it was before you fired your rocket motors. So there's no way to measure your steady speed in a vacuum except using the Doppler shift of radio transmissions. Radio waves travel at a fixed speed in a vacuum. So this means that the waves will always appear to travel at the same speed relative to you, no matter how fast you are going. In any case, what does it mean? How fast am I going? Now, this constancy of the speed of light, radio waves, led Einstein to his theory of relativity in 1905. Well, this is all very interesting, but it is of little consequence to us radio amateurs. We just want to use radio waves for communication. So how do we make them? Well, of course, we use an antenna. And the simplest antenna is the dipole. One of the consequences of the fact that there are two sorts of charges, positive and negative, there is no such thing as a monopole. Monopoles simply don't exist. You can't make radio waves which out of a monopole. You can't do it. A dipole is the simplest possible antenna. So let's talk about dipoles for a bit. By the way, monopole antennas, which are really dipoles, in which one of the elements is a reflection of the other in the ground plane, as shown on this, this diagram here, the gray area is the ground plane and the vertical element is the monopole. Well, actually, what you've got is a vertical dipole, because the reflection in the ground plane, rather like a reflection in a mirror, gives us a dipole. And it's called a monopole because it has all of the, in the horizontal plane, there is no variation in the gain in any direction. But of course, there is no end fire. It doesn't fire straight up. it is really just a dipole, except being vertical. So here is the dipole. A dipole is just a two-element balanced antenna. The element lengths are not necessarily equal to a quarter of a wavelength. In fact, I seem to remember spending a great deal of my time as an undergraduate studying very, very short dipoles, which are much, much shorter than a wavelength, which are called Hertzian dipoles. But the nice thing about a half wavelength dipole, in which each of the elements is a quarter of a wavelength, more or less, because there are end effects and you have to take account of this and that. But the feed point impedance is then about 72 ohms and is entirely resistive. That's an example of a resonant antenna. Now, at the center of the dipole, the current is maximum and the voltage is minimum. And therefore, the impedance is low if you feed it there. Voltage divided by current, that is the roughly the definition of impedance. So if you've got a high current and a low voltage, that's low impedance. At the ends of the dipole, the current is minimum and the voltage is maximum. Therefore, the impedance is high if you feed your dipole there. Now, if you're feeding your dipole using a balanced feed, such as an open wire line, then you should connect the two feeder wires directly to the dipole elements. If you're using a coaxial feeder, as most of us do, then you must use a balanced to unbalanced transformer at the feed point. If you do not do this, your arrangement will still transmit and receive radio waves, but the whole of the outside of your coaxial line, right back to the transceiver or antenna tuning unit, will be part of the antenna. You will no longer have a dipole antenna in which all the parts are up in the air, but you will now have one side connected to another element, the outer of your coaxial cable, which goes right back down to your shack. It will waste power on transmit and will pick up noise on receive. So using a balun at the feed point is very important. Some antennas are fed at one end, some dipoles are fed at one end at the high voltage point, high impedance point. If you're doing this with a 50 ohm coaxial cable, you probably will need to use a transformer. I've seen them, for example, having a 9:1 turns ratio. Impedances transform as the square of the turns ratio. So impedance transforms therefore as 81:1, and your 50 ohms transforms to about 4,000 ohms. So we have therefore the two things. If you feed in the middle, you've got about 72 ohms. If it's a quarter wave transformer. If you feed at the end, it's thousands of ohms. Now, the electric and magnetic parts of the radio wave are equally important. So you need to get as much of your antenna as high as possible, not just the high current parts. So let's first think about how you transmit radio waves with your antenna. And here we have an important principle, which I'm sure we're all aware of, really. It's the appreciation that power in a system is only absorbed by resistive parts. Power is only absorbed by resistive parts of the system. Pure inductances and pure capacitances do not absorb any power on average over a cycle. Now, we all know that we have inductors which get hot, and capacitors which get hot, electrolytic capacitors especially, but that's because they're not pure. Inductors have resistance associated with them, and that resistance is the bit that gets hot. And capacitors have losses which are like resistance, and that produces heat as well. So in a pure system, the inductance and the capacitance, they do not absorb energy. It's only the resistive part. So when you transmit, where does the power go? Well, it goes into the resistive parts of your radio system. So resistive losses in your equipment, losses in the surroundings, heating up your garden, and also in power radiated away in radio waves. Now we model the power being radiated away using the concept of radiation resistance. The power lost to the resistance is just like a resistance, except that nothing locally gets hot as a result of your transmission. There is also a reactive, which is lossless, a reactive lossless component like a series L or a series C, unless the antenna is resonant. And you can tune this out using an antenna tuning unit. So the equivalent circuit of your antenna system is therefore like this. Now here you can see a series resistance, well in fact two resistors, RRAD, the radiation resistor. Any power dissipated in that goes into radio waves, and that's in series with another resistance, R loss, and any power that you put into that actually is lost. It does not get radiated away as radio waves. And then there is this X, which is the reactance, which might be capacitive or inductance, but which doesn't do, it doesn't absorb any energy. It just gets in the way. It's an impedance, and so it impedes the current flow, and so you can't get quite as much energy into your RRAD as you wanted to. But you can tune that away by using an antenna tuning unit, for example, or by matching at the feed point, something like a gamma match, for example. So by tuning away the X part, you really are left with just these two resistances, one of which is a mythical resistance, an imaginary resistance, which we call the radiation resistance. And that's the bit you want to dissipate all your power in. And then you have the wasted bit, which is to do with resistance in your wires, resistance in the garden, you know, heating up the soil in your garden, that sort of thing. Now, the next thing to consider is the radiation pattern. Now, this is just a plot showing how power is radiated in each direction, and it's usually expressed as a ratio with respect to the main beam or to a reference antenna. Now, what I've shown here is the radiation pattern of the dipole antenna. You are to imagine that you're hovering above the dipole antenna, which is the horizontal red line on the diagram. So you're in a helicopter or something a long way above. And then the light red curve shows how effective your dipole is in radiating in any particular direction. And there's a graticule underneath in gray so that you can see actual values. Now the graticule is calibrated in decibels, dBs, where the outer ring is 0 dBs. And dBs are sometimes rather confusing for people. So the way I remember to deal with decibels is that a decibel is just a ratio of power. The scale is logarithmic, but we needn't worry too much about that. The fact is that 0 decibels represents a power ratio of 1:1. And we've calibrated the diagram so that the main beam, which is this this direction here, and also this direction here, if this is east-west, then these are the north-south directions. We've made it so that the maximum is right on the graticule, so that that we'll call 0 dBs, or a power ratio of 1 to 1. So now that's that point there. If we come down to this point here, which is -6 on the scale, that's -6 decibels, and that's a power ratio of 1 to 4. And that's an interesting point because that represents a 1S point. When you go from S7 to S6, you go down 6 dBs in power, or a ratio of 1 to 4. Another interesting point is 12 dBs. That's 2 S points, and that's a power ratio of 1 to 16. So this direction over here, which I've shown, what is that? That's, you see, this is about 50 degrees, isn't it? 50 degrees off broadside. If broadside is straight up, then that's 50 degrees round. Well, you can see that that direction crosses the red curve at around about -5 dBs. Little more than -5 dBs, so that's nearly 1S point down. And this direction over here, well, you can see that that crosses the red curve at around about -15 or so. So bearing in mind that 12 dBs is 2S points down and 18 dBs would be 3S points down, then that's about 2.5 S points down. So you can see that having a diagram like this, if it really represents your antenna, you can get a good idea of how effective it is at firing off radio waves as a function of direction. Now you also have to consider the antenna pattern in elevation. This is not a dipole. This is a much more complicated antenna. In fact, it's a multi-element beam. And for this particular multi-element beam at this particular frequency, mounted at this particular height above the ground, with the characteristics of the ground, would have a beam pattern something like this. Now this time the vertical direction on the diagram, the one with the scale on it, is straight up, and you have the horizontal direction as the line, the horizontal line at the bottom. And the green dot is at the point of maximum radiation. That's the point we've called 0 dBs. And you can see that that's about 10 degrees elevation. However, this diagram is more complicated in that you can see that there are these other lobes. There's a second lobe here at this particular direction. It's only about half an S point down. So although you've got the best direction is at an elevation of about 10 degrees, you're actually firing quite a lot of power off at a higher elevation. And then there's a third lobe and a fourth lobe and a fifth lobe. And we call these other lobes side lobes, so that the main lobe is the one that you're really interested in, and the side lobes really fire off power in directions that you don't particularly want to fire them in. They actually waste power. So to summarize then, the simplest pattern that you can have is that of a dipole. Larger antennas can be thought of as being made up of 2 or 3 or 10 dipole elements, and the dipole elements may be shorter than λ/4. The electric and magnetic fields of the individual elements add together as vectors, taking into account the amplitude and the phase. So supposing you consider one little dipole element and another little dipole element, each gives rise to a field, and the oscillations from the two they add together, the amplitudes and the phases add together as vectors. Now, this is perhaps quite a difficult concept unless you're very used to thinking about that. But roughly speaking, you can think of two oscillations which are in phase. Here, I don't know if you can see my fingers going up and down. So here's the one, and here is the other, and they are going up and down in phase like this. And the amplitudes then add together. So if this one is 1 amplitude and this one is an amplitude of 1 as well, 1 and 1 makes 2, and the total amplitude would be 2. By the way, the power is proportional to the square of the amplitude, so that would be 4 times the power. Now, somewhere else in another direction, the first one and the second one may be oscillating in antiphase. And these add up to nothing at all if they're equal in amplitude. So you can see you'd get a null along that direction from the two elements. And this is why you get these complicated antenna patterns, because of the way the fields add up vectorially, as they say, which means that they add and subtract according to the phases of the things which are being added together. So now we must also take into account the images reflected in conducting surfaces, such as the ground, as well as the real conducting elements themselves. This is very important, and it's perhaps not always appreciated. You know, you may think that you have an antenna, which maybe a Yagi or a dipole or whatever it is, but that is up in the air over your garden. And the garden, if it's really, really wet and flat, can be thought of as a mirror. And so what you've actually got is the real antenna up in the air, and then the image of the real antenna in the ground. And both of them have to be taken into account if you want to work out what the real antenna azimuth and elevation patterns are. Of course, most of the time we're not concerned with this at all. We sling a piece of wire in the air and have a go, and gosh, he can hear me S9. That's wonderful. So this is all perhaps a little bit theoretical, but nevertheless, you need to consider what your ground is like. And if your ground is very lossy, then any radiation in that direction, or rather any electromagnetic field in that direction, just produces heat and represents a loss in your system. Now, the other thing to remember about antennas is that gain is a relative term. A gain of 10 dBd means that your antenna fires 10 times more in that direction than a dipole would, the little d representing a dipole. So you've got an antenna which in that particular direction fires 10 times more power than a broadside on dipole would fire in that direction. But remember that if you've got an antenna with a gain of 10 dBd, it only has that gain along its main beam. And you might have a gain of minus 10 dBd along another direction. So having a complicated antenna means that you have to be careful about lining it up. Now, what about receiving? Well, your antenna characteristics, the gain, the radiation pattern, the radiation resistance, are exactly the same for transmitting as they are for receiving. So this makes it nice and easy for us. Tune your system for transmitting, and then you're all set for best reception. You don't need to do anything else. But what does it mean to have a radiation resistance when receiving? Well, you can imagine, I suppose, that the incoming radio waves develop a corresponding RF voltage across the radiation resistance. It's a bit like having a signal generator in series with the radiation resistance. And when transmitting, you can imagine that your transmitted power is dissipated in the radiation resistance. So we have this reciprocal relationship. Now, when transmitting, you want to maximize the power dissipated in the radiation resistance. And this means reducing as much as possible the losses in your antenna, the losses in your antenna tuning unit, your feeder, usually coax, in your antenna wires, the resistance, and in the surroundings. The electromagnetic fields responsible for losses in your surroundings diminish as the square of the distance. So as high as possible and as far away as possible are usually good strategies. But we all know that amazing results can sometimes be obtained with a bent coat hanger slung out the window. And why is this? This is because, first of all, we have amazingly sensitive receivers. And a loss, this is quite extraordinary really, a loss of 98.4% of your transmitter power to waste actually is only about 3 S points. So you go from an S8 to an S5, an S9 to an S6 with your piece of bent coat hanger thrown out of the window. Okay, well now, how do we get maximum power into the antenna? And this is not as difficult as you might think. Well, we know it isn't because we all do it. The first thing to appreciate is you don't have to use a resonant antenna. If you can get as much current flowing in your bit of wire, which is non-resonant, as if you had a resonant antenna, you would do just as well. But this might require using an ATU, an antenna tuning unit, of very high quality. What about a mismatch at the antenna feed point? Well, this causes some of the power to be reflected so that you then have standing waves on the line. Your voltage standing wave ratio, VSWR, would then be greater than 1:1 if you have a so-called flat line where you only have a forward traveling wave and nothing reflected. Then that's the ideal, and you'd get a VSWR of 1:1. But it doesn't matter as much as you might think from reading all the literature on the subject. There's so much about antenna matching that you might think that that's the holy grail. Well, it's not actually as important as you might think. Just take a look at the curves on the right-hand slide, the right-hand side of the slide. The first one to look at is the horizontal red line. Now, vertically, we've got attenuation. I can't read my own writing here. Attenuation in decibels. And horizontally, we've got a standing wave ratio measured at the load, at the antenna feed point. Now, these curves are curves representing different feeder losses. So let's start with the red curve where you have an ideal feeder. It has 0 loss in it. You can never get one of these. I don't know where to buy them, but we can think about them in theory. In that case, the VSWR at the load can be as bad as 10:1. There is no additional attenuation from that. The VSWR only becomes important when you use a lossy feeder. But actually, the feeder has to be really quite lossy. Let's suppose you had not spent very much on the quality of your coax, and you had a feeder, a length of coax with a loss of 3 dBs. Now that means that whatever you do, whether you have a flat line or not, half the power goes to heating up the feeder. Now that's the black curve here. You can see it's marked 3 dBs. And what this diagram shows is the additional attenuation, which you get in addition to the 3 dBs because you have a feeder which is getting hot. And the additional attenuation in that case, well, we can see that if you had, for example, a VSWR of 7:1, so I don't know if you can see my pointer here, but there's the line VSWR 7:1, which is a pretty high standing wave ratio. And we come up here to where it crosses the black curve, and you can see that's just about 3 dBs. So a VSWR of 7:1 would only give you an additional 3 dBs. So you've got 3 dBs anyway because your feeder is getting warm. And you have a VSWR of 7:1 because there's a big mismatch at the end of the feeder. That gives you an additional 3 dBs, and the total is 6 dBs. That's 1 S point. So by not spending very much on your feeder and by being very careless about the matching at the feed point and having a VSWR at the feed point of 7:1, you've only lost 1 S point. Now, I think that that's really quite interesting and quite surprising. But the take-home message is use a low-loss feeder, spend as much as you can on the feeder, and make sure you use a good quality antenna tuning unit, but don't be too concerned with getting an exact match at the antenna feed point. Now, by the way, the VSWR is what you measure at the antenna tuning unit down near the transmitter. You don't usually measure the VSWR high up in the air where your antenna feed point is. And you can be misled depending on how lossy your feeder is, because if you think about this, what's happening here is you have a forward wave going from the transmitter to the antenna, and you also have a reflected wave which is coming back down the feeder. And by the time that gets back to the point where you actually measure the SWR, in other words, at the ATU, by the time it gets there, the reflected wave has also been attenuated. So the net result is that the SWR, which you measure at the transmitter, looks much better. It's encouraging. It looks much better than what it really is up in the air. And we can see that on this diagram. So we've got on the vertical here, we've got the VSWR at the sending end. This is what we measure. And on the horizontal line, the VSWR at the load, this is what the SWR meter would measure if it was up in the air, actually right next to the point where the feeder is connected to the antenna. So here we are. Here's the black curve is the not very expensive 3 dB lossy feeder. And you can see that our 7:1 VSWR at the load would actually produce only about, well, it's about a little over 2, isn't it? A VSWR of 2 down at the transmitter end. So you get good encouragement, but just bear in mind that it is optimistic. Well, now, what about resonance or lack of it? I've already said, I think, that actually resonance is not required to have a good antenna, but it just makes it easier because resonance means that you haven't got the X component in this diagram here. The reactive component is 0 for a resonant antenna. So your antenna tuning unit has a much easier job of it. Now, what about multi-element antennas? Well, now, these come in two sorts. First of all, there are the parasitic element, multi-element antennas, like the Yagi, for example. These antennas have one feed point, so one driven element, and you can understand how they work actually really quite simply. In fact, you can demonstrate it on your kitchen table. How many people remember Barton's pendulums? I remember being shown these at school, and I had no idea at the time that I was actually being shown how to understand the Yagi antenna. So here we are. You can do it yourself. Here are Barton's coupled pendulums. Get yourself, well, I've shown here a couple of retort stands, as they used to be called in my school days, but get yourself a couple of points from which you can sling a piece of string loosely, like a washing line, and then hang on to that string some pendulums of different lengths. Now, one of them should have a much larger weight than the others. It's the driven element, and I've shown that in red here. One of the pendulums should be longer than the driven pendulum, and the rest of them should be shorter. And what you do is you set the red one, the driver, swinging to and fro, in and out of the page as we look at it. Well, what happens? The pendulum swinging actually causes the washing line at the top to wiggle backwards and forwards, and it causes the other pendulums to start swinging. And after a time, you will notice that the longer one, the one which is longer than the driver, actually is swinging 180 degrees out of phase with the driver. And all of the shorter ones also swinging, but they're all swinging in phase with the driver. Well, this is exactly what happens when you have when you have a Yagi antenna. So here is your Yagi antenna. The driven element, let's say it's lambda by 2, marked there. There's the driven element. And over here is a slightly longer one. And we know from Barton's pendulums that the current in there, which is induced by the radio wave being launched, or the electric fields, electric and magnetic fields, I should say, launched by the driver, they cause a current which is 180 degrees out of phase with the electromagnetic fields at that point. So this driver here re-radiates a field which is 180 degrees out of phase with the field that's going by. So it adds up to nothing in the reverse direction, giving us a null in the reverse direction because the field from the driver and the field from the reflector cancel. But if there is a quarter of a wavelength or thereabouts between the driver and the reflector, then by the time we've taken account of the phase lag of 90 degrees and then 180 degrees and then 90 degrees again, then the field from the reflector actually is in phase with the field from the driven element in the forward direction. So they reinforce. And then the shorter ones here all oscillate in phase. They have currents which oscillate in phase with the passing field. And so they reinforce as well. And so you get a Yagi antenna with fields reinforcing in the forward direction and cancelling in the reverse direction. That's obviously a rather simplified view of the Yagi antenna, but nevertheless, that's the basis, I think, of how it works. So you can demonstrate that on your kitchen table. And I do suggest you do it if you haven't seen it, because it isn't quite what you would expect. Now then, the second sort of multi-element antenna is the so-called phased array. And in this case, the beam direction of maximum, the beam shape, can be changed by changing the phase of the drivers. Now, in a multi-element phased array, each of the elements is actually driven independently, and they can be driven independently with a phase difference. Now, I had a narrowboat. We've sold it now, but for 19 years we had a narrowboat, had a wonderful time. And I thought, well, it was just the right length, actually. It was made of steel, of course, which is quite good for reflecting. And I thought it'd be good to try out a 2-element phased array on the narrowboat. So I had a vertical mounted at the front of the boat and a vertical mounted at the back of the boat, and they were about 8 meters apart, which is, well, on 20 meters, what is 20 meters? Well, it's around about a half a wavelength. Now, this diagram on the left here, you can imagine the narrowboat is east-west. And the 2 elements driven 180 degrees, driven in phase, would give rise to nulls in the east-west direction, because the being about half a wavelength apart means that the wave from one would cancel with the wave from the second one as it went by. Whereas, of course, broadside on, you get a maximum. So this is the sort of pattern that you might have expected from my narrowboat when each was driven in phase. And then with a 90 degree, well, actually the next one to look at is the right-hand diagram, where they're driven in antiphase. So 180 degrees out of phase with each other gives you then a cancellation broadside on, so you get a null in this direction. But of course, since they're half a wavelength apart, you get reinforcement in this direction. And this is what happens with a 90-degree phase difference. Now, I should say that although I set all this up, and it was all very exciting, very interesting, actually it was jolly difficult to do, because one of the problems with having elements close together is that they affect each other, so that the actual impedance that you get at the feed point depends upon the state of the other element. And I was using actually screwdriver antennas, 2 vertical screwdriver antennas, and it was really very difficult to set it up. But never mind, it was a good experiment to do. These diagrams, by the way, are entirely theoretical. I could never establish in practice whether I was getting anything like the same thing. So perhaps I should finish with looking at another phased array. And this one, phased array, actually very close to my heart, because this is a picture of the 4.5 acre array at Lord's Bridge near Cambridge, where I did my PhDs all those years ago. And it's actually the array which was used in the discovery of pulsars. This one has 2,048 full wave dipoles arranged in 16 east-west rows, each row having 128 dipoles. And they're spaced, and each row is driven with a different phase, so that for reception only, the beam can be pointed straight up or can be bent away from the vertical to point at different elevations between 20 and 90 degrees. So I look at that diagram and sob peacefully to myself. And actually, it reminds me of the biggest problem that we had with this particular phased array. And do you know what that was? It was keeping the grass cut underneath. You can see that if you were to drive around with a lawnmower with a spark plug sparking away, it might rather well, in fact, it did. It certainly did. It was by far and away the brightest thing which could be seen with the array. So we solved that problem simply by getting the local farmer to keep some sheep underneath the array. And that's how the grass was kept short. And on that note, I'll pass it back to you then, David.
Lovely. Do you know what? When you were saying that, I was thinking, how are they going to cut all that grass? It's like when you see all these solar panels as well, and you wonder how they're going to deal with that. And sheep are a perfect answer, aren't they, for that? As long as they weren't transmitting with them. Anyway, it was really good. Thank you very much, Peter. Well, I'm sure that's inspired lots of people and asked maybe people have got questions, comments and things like that, because you've certainly given us a lot to think about there. So if you've got a question or a comment for Peter and you haven't already done so, please ask it now on either YouTube chat or BATC messaging. Please don't forget to include your first name and your call sign, if you have one, within every message. So Peter, I mean, has this been it almost feels like a sort of life's work, looking at exactly how antennas and radio waves work. When you were thinking about it, ready for this presentation tonight, is there much that you've sort of learned extra in the more recent years?
Well, I think one thing that I quickly learned all those years ago was that you never really understood something until you had to explain it to somebody else. And I think that having to, for example, put together lectures for Cambridge undergraduates or teaching them on a smaller class basis, actually explaining really quite difficult concepts sometimes to other people is the way that you yourself begin to understand what's going on. And I think over the years, actually doing the hobby as well, actually putting up antennas and making measurements and actually trying to understand what the individual things mean. What it's taught me really is that things are much more complicated than the rather simple view that I have perhaps put across tonight. But nevertheless, the basics are still there. Yeah.
I mean, what I always ask somebody is, often I meet someone who knows so much actually about radio waves and antennas and everything. But what I do ask is, do you think there are new types of antennas yet to be invented, yet to be discovered or developed? Or are we there with all of our various Yagis and dipoles and things like that?
Well, that's a very interesting question. And I think probably the answer is yes. I actually, a few years ago, had to look very seriously at a proposition from somebody who seemed to be suggesting a completely new way of creating radio signals. Well, not just radio, but electromagnetic waves. And it set me thinking, because of course, we're all going down tram lines. We read the books. We know what other people are doing. We have been doing it like this for years, and it works. And actually thinking outside the box and stepping outside the box and finding a new way of doing things, it's exciting. And of course, it hasn't been done yet, but I would not be surprised to find that actually somebody makes a breakthrough.
Any ideas what that might be? I mean, have you had any thoughts? I'm sorry, I'm just asking you, because it does occur to me in every other field of electronics and things that there's been huge discoveries and developments, but I mean, not that I know everything about all the aerials, but they are the same old types of aerials, really, it seems, going back for years and years. You look at the older radcoms, the radio constructors and things like that, they were always talking about the same sort of antennas we're doing now. And so have you got any ideas?
Well, I think we'll probably find a whole new generation of antennas will come about when people are able to buy, for not very much money, superconducting wires, which have no loss at all. And I bet that antennas made with superconducting wires will have really rather interesting and different characteristics.
I mean, in theory, there shouldn't be any losses through heating, and as you've mentioned, a lot of the losses at the moment are through heat, or most of it is. So if there isn't the heating, if there are no losses, then they're perfect conductors. Is that what you're saying? So there could be new types of antennas come from those?
Well, yes, well, certainly new to radio amateurs. I can imagine, for example, that one might have a very thick superconducting wire in which it arranged in such a way that the currents were actually going round and round the outside of the wire rather than going along the wire. This would have perhaps an interesting characteristic, but more than that, I cannot say.
No, it's all right. Well, I'm just teasing you, really, I suppose. But I mean, superconductors and, well, anyway, we have got a few comments and questions from people. So if you have got any at home now, do start asking them, because otherwise we'll be finishing. But a couple of things. Firstly, actually, SM7UDB, Mikhail. Good evening from Sweden. I wonder if Peter can guide how to make the phase shift for a phased array. I know with a coax, just a couple of minutes, I know with a coax, but it must be possible with a capacitor, as for the HB9CV.
Well, yes, certainly if you're going to do this, you need a lot of patience, and you must understand what you're doing. It's no good just sucking and see. You actually have to calculate very carefully. But there are arrangements. There were arrangements which came out of the last century, World War II type things. For example, having inductors which change their orientation with respect to each other. So, for example, supposing you had a coil, and inside that you had another coil, and you were able to rotate the inside coil about an axis at right angles to the outside coil, then in one orientation where the two were parallel, you would get the same phase coming out of the inside coil as you were putting in the outside coil, but then rotate so that now the inside coil is pointing in the other direction. Well, then that would be 180 degrees phase difference. And as you rotate in between, so you would get different phases between the two. So that's a sort of magnetic way of doing it. I think the electric way of doing it is more complex. And of course, anything you make with coils and capacitors are resonant. And so you might set up something which works very well at one particular frequency, but then if you wanted to change frequency, you'd have to have another arrangement. That would all make it more complex. The usual way of doing it in radio astronomy, when I was, all those years ago, when I was working on the 4.5 acre array, was with cables. So we had something called a Butler matrix, which was invented by Mr. Butler, I think, which was an arrangement whereby there were 16 inputs and 16 outputs, and all the inputs were joined together to the outputs with cables of various lengths, such that there would be a phase difference of 0 or 10 degrees or 20 degrees or 30 degrees, whatever it was, between the inputs on one side and the outputs on the other. But that was because of the time taken for signals to travel down cables.
Yeah, thank you. And it may be relevant to Mikhail. I don't know if you're a member of the RSGB, or Michael, sorry, but there is an article in this month's of the latest antennas on the HB9CV antenna. It's in this latest Radcom, so just happened to be reading that earlier on, so that may be helpful to you. Next question from Jeff, 8NT. What about magnetic loops? How effective are they? Especially the importance of location, salt water, that sort of thing, you know, salt water around the area.
Okay, so you're talking to a magnetic loop enthusiast. I've moved now to this house, which is a little bit bigger than the flat that I was in. The flat that I was in had an upstairs attic, and in that I had room just for a magnetic loop antenna. This was actually a baby loop. I don't know if you've come across baby loop. It's a lovely thing. It can tune anything from 6 megahertz to about 30 megahertz. Now, the thing about a loop antenna is that it is a highly resonant structure. Because the loop is physically small with respect to the wavelength. I mean, operating at 20 meters, for example, if you have a 1 meter loop, well, it's only 1/20th of a wavelength across. So it's highly resonant. So the currents which flow are very large, and therefore the losses due to resistive losses in the loop are very important. Furthermore, because it's a small antenna, it has a very small radiation resistance. Generally speaking, the radiation resistance goes down dramatically with size below about half a wavelength. So a small loop might have, I don't know, half an ohm of radiation resistance. And unless you can get the losses of the resistive material which make up the loop down to something comparable, then you are mostly just heating up the loop. But if you can get them down, and the baby loop actually did quite a good job, if you can get them down and you operate on the point of exact resonance whereby your X in the diagrams that I showed earlier, it was 0, then they can be really effective. I mean, people are always reporting how effective they are, and I certainly can endorse that. And the other thing about a loop, of course, is that you can mount it on a turntable and turn it round, and that's just like having a dipole. In fact, the radiation pattern of a loop is a dipole. As a dipole pattern, it's just like turning it round so that you're actually pointing the null, in particular, along the ends of the dipole in a particular direction if you want to reduce the signal from that direction. As for whether they're effective or more effective or less effective over particular sorts of ground, I don't think that there's anything special about a loop as compared with any other antenna. The ground has to be taken into account. In the case of my loop, I was up on the 2nd floor, well, actually the 3rd floor by the time we got to the attic, 3rd floor above ground, and so therefore 6 floors below there was the image of the loop that was in the foundations of the of the structure somewhere. I think that if you were able to use your loop right by the sea, then you would have the advantage of a conducting ground. Use it on a boat, even better. Nice conducting ground. So one thing I discovered with the narrowboat was that the people said to me, "Oh, well, you're doing all right, aren't you? Because there you are, you're floating on the water, and the water is a good conductor, and so you've got an ideal ground." Well, actually, that's only true if you're at sea, because water inland is fresh water and is really not a very good conductor at all. But anyway, I digress.
Oh, that's good. Jeff's in Belgium, so I hope that's helped you, Jeff. We've got a question now from one of our newcomers to the hobby. This is Paul, M7XIX, and he asks, what's the best way to get on 80 metres with a small back garden, approximately 15 metres long, 8 metres wide?
Yes, hello. That's That's a good question. So 80 meters is difficult for a number of reasons. One is that the wavelength is very long, and so therefore any antenna that you make is almost necessarily short compared with the wavelength. And that means that it has, it's going to have a smaller radiation resistance than say a half-wave dipole. And in addition to that, 80 meters is plagued with interference from your, usually from your house first, and then from other houses round about. All of the switching power supplies and VDSL and all of that all make themselves felt on 80 meters. And certainly when I've tried 80 meters, what I've usually discovered is that I can't do very much because I'm trying to battle against an S9 noise level. Even before we start, the S meter is hovering there around the 9 level. So one of the ways of dealing with that is actually to use something like FT8, one of these digital modes, Whisper, FT8, things like that. If you haven't explored them already, they're well worth exploring, because what they do is operate with very narrow bandwidths and enable you to get down 20 or 25 dBs below your noise level. And bearing in mind that 18 dBs is three S points, and 24 dBs therefore is 4 S points, then your S9 noise level goes down dramatically, effectively, when you're using one of these digital modes. So although you may find that you have a high noise level at 80 meters, you can nevertheless do things with the digital modes. As far as the antenna itself is concerned, when I started on 80 meters, and I had a piece of wire. I had an upstairs bedroom, and I had a piece of wire slung out the window to the tree opposite. I seem to remember I caused a lot of television interference roundabout, but I was able to do quite a lot just with a simple arrangement. But remember, the thing is to get it as high as possible and as far away as possible. So use a reasonable quality coax and a balun, of course. If you can put up a balanced antenna, you will probably get better results with that than if you're using an unbalanced antenna, which automatically means that the other half of it is a reflection in the ground or something else.
Yes, thanks, Peter. I think the other thing, if I may suggest to Paul, that there's a good book by the RSGB, actually by Steve, G0KY, a mutual friend of ours, called Stealth Antenna. And that's really well worth it, especially if you've got limited amount of space, even antennas in the lofts and things like that. That's called Stealth Antennas, and you can get it from the RSGB bookshop.
And I have a copy, and it's very good.
And so have I. I must admit, I've had both of the editions of it. And it isn't just because it's a friend who's written it as well, but it is a really good book. About £12 or so, I think. Now another question from William, GI8WFA. How can you discriminate between the E field and the H field?
So I would ask William, hi by the way, why you would want to discriminate. The radio wave has both fields. So I'm not sure what discrimination would be. You can imagine in your dipole, for example, that the E field is parallel to the wire and the H field is in loops around the wire. You could imagine these loops breaking away from the antenna and going off as radio waves. But the radio wave itself has as much power in the E as the H. So there is no discrimination between the two. If you're transmitting radio waves, you're transmitting both, and both are equally important.
Yeah. Well, I hope that's helped you there. Another question, sorry I don't have a name, your YouTube name is Ace Studios. I'm fortunate to have a plot long enough to accommodate a dipole for 160 metres, but can't, which is nice, isn't it? But can't raise it more than 30 feet. Is it worth trying, please?
Yes, 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 yes. Always try. I'm an experimental physicist, and I would always say that you should try. Although it's only 30 feet off the ground, it means that you can think of the image of your antenna as being 60 feet away from the antenna and below ground. And that means that your radiation pattern will be much affected. The image also is in antiphase, by the way. So it means that your 160 meter antenna will fire mostly directly upwards. And horizontal will more or less be, it'll just reinforce itself as zero. It'll null out horizontally. So it'll be mostly firing upwards, but that's fine for 160 and 80 and even 40 during the daytime. Vertical radiation is probably what you want. So yes, do give it a go, and remember to buy yourself some good coax and take the coax all the way to the middle of the antenna, which will be quite a long way away from the house, and make sure you use a balun so that your antenna then acts as a dipole. And I think you'll have terrific fun.
It sounds good. Well, I hope that's given you inspiration. Peter, thank you ever so much for this evening. I must admit, Pete, for me personally, and I should know better maybe, but just the explanation of what gain was about for an antenna, because I remember when I first started this a long time ago, I thought, well, how can a non-active device have any gain? But you immediately telling me that everything is referenced from a dipole. That's going to stay with me. That's been really useful. And I want one other word from a gentleman or a lady called Hibby. MM0RFN says, so far this is proving to be a great explanation of some of the full syllabus, and I look forward to recommending it as a supplementary material for our students. So that's from a trainer. So,
oh, well, thank you.
It really has been really very interesting, Peter. I'm sure you're going to get us all wondering and experimenting as well with antennas, which is what it's really all about, isn't it? And thank you very much indeed for tonight.
Well, it's been a pleasure, I must say.
Thank you. And that concludes this webinar. And thanks once again to our guest, Peter Duffett-Smith, GM3XJE. Thanks also to our studio director, Tammy Palmer, M0TC, and the RSGB team who helped put this series together behind the scenes. We hope you've enjoyed this Tonight at 8 and that you'll be able to join us next time when Mike Richards, G4WNC, will give us a presentation on conversational data modes. And if you'd like to see details of this and other future webinars or recordings of past editions, please visit rsgb.org/webinars, where you can also send us comments and feedback. And a reminder that if you subscribe to the RSGB's YouTube channel, you'll be notified of all upcoming Tonight at 8 webinars, as well as other new videos and presentations from the Society on a wide range of amateur radio topics. But until next time, this is David, G7URP, signing off and clear. Bye-bye.